Well, in this video, we're going to break out of circuits consisting only of resistors and sources. We're going to talk about, more generally, circuits having capacitors and inductors. This will open the door so we can handle any circuit that we want. Now, if we go down the path we went through with resistor circuits, and we use the VI relations, KVL, and KCL, it turns out what you're going to wind up with is a differential equation to solve. I'll show you that. And that turns out does not give us much insight into how the circuit is working, what they're doing, why were they designed this way, how do I change designs. We're going to introduce a new idea, something called impedance, which is going to allow us to think about every element in the circuit as being a kind of resistor. That means we can use current divider, voltage divider, all the techniques we've already learned with resistors. That's the promise. Let's see how that works. So here's a simple circuit. It's what's known in the trade as an RC circuit. That terminology means it has one resistor and one capacitor usually. And here they're connected in series. So the source here is some voltage, or whatever it may be, and I've decided to take the output to be the voltage across the capacitor. Okay, so what we want to do is find V out for any Vn. That's the thing we have to do to solve the circuit. Well, let me remind you what the VI relation is for the capacitor. The current is proportional to the derivative of the voltage. So we need to see how that comes in to solve the circuit. So remember, that current I has to be, for this VI relation, has to be going in the positive side of voltage. And V is now V out. Because for this circuit, that's what we're playing with. So what I'm going to do is write KVL. I'm going to start here and go around like this. And we know from KCL that the current through the resistor is also I. So when I write the KVL equation, V out is equal to, well, I want to go plus to minus this way, and that's voltage in that direction is minus Ri. Okay, from the VI relation. Current's going in the negative side, not the positive side. We have to flip the sign. Plus Vn. Well, now I'm going to substitute for I in there, and we get minus Rc dV out by dt plus Vn. Okay, so if I bring the derivative over to the other side, we wind up with the input-output relationship for this circuit, and it's what's known as an implicit relationship. This is the relationship, but you have to solve something. It isn't directly given to you like it was for the resistor circuits. So Rc times the derivative V out plus V out has got to be Vn. So now what you have to do is you tell me what Vn is. It could be a sinusoid, a pulse, whatever. And now I have to solve this differential equation for each case. Well, it turns out that's a little tedious and doesn't really tell us what's going on. So I'm going to take a different approach so we're not going to solve differential equations in this course. We're going to sneak around them and figure out a better way to solve them. So this is a very different approach, which is based on a somewhat surprising assumption. Just suppose the voltage source is a complex exponential. So Vn of t is equal to capital Vn. This is known as the complex amplitude. Could be a complex number, but it's just a number. The only part that varies with time is the complex exponential, e to the j 2 pi ft. Okay, so we're just going to assume that for right now. Well, here's the claim, that every voltage and current in the circuit, once you solve it for the complex exponential source, also turn out to be complex exponentials. Every voltage and every current is of that form. So what I want to do now is check to see if such a solution is consistent with the VI relations and with KVL and KCL. So let's do the VI relation. So let's start with our resistor, where the VI relation is voltage is equal to the resistance times the current. And I'm just going to plug in the voltage and the current in here. And turns out it is consistent as long as the complex amplitude of the voltage is R times the complex amplitude of the current. Now, the other thing to notice is I can cancel these complex exponentials. And there is explicitly the relationship between the current and voltage complex amplitudes. This is an interesting point about this cancellation. So let's talk about a capacitor, I equals C dV dt. So here's the current I, and the derivative of this is just J2 pi f times the same thing because of the properties of the exponential, and we need to plug in the capacitor value because that's what's over here. So again, with cancellation, we now find that this assumption is consistent as long as the amplitudes are related this way. The amplitude of the current is equal to C times J2 pi f times the amplitude of the voltage. And I'm pretty sure you can believe that for the inductor, a similar kind of thing is going to happen. Amplitudes are related by a different formula, but still they're related. Okay, this cancellation is really important because let's think about defining a quantity Z for each element that is the ratio of the complex amplitude of the voltage divided by the complex amplitude of the current. This is known as impedance. So we're assuming that the source is a complex exponential at some frequency, and we now know that every voltage and current in the circuit is also a complex exponential. Well, let's sort of hide the complex exponential for a while and just look at the complex amplitudes. We're going to define Z, the impedance, to be capital V over capital I. I want to point out that V is in volts and I is in amperes, so the ratio is ohms. Okay, so impedance is got units of ohms. However, for the capacitor and the inductor, they're complex valued. So the impedance of a resistor is just the resistance, but the impedance of the capacitor is 1 over J2 pi Fc. Impedance of the inductor is J2 pi Fl. Okay. So what this means is that we can think about every element in the circuit, resistors, capacitors, inductors, as being complex valued resistors, which is going to be the key thing. But we've now just checked the VI relations. We've got to check KVL and KCL before we get to figure out the consequences of that. So it looks looking good, but when you look at KVL and KCL, you see that everything hangs together again, because if every voltage in the circuit is a complex exponential, always at the same frequency, but they have different amplitudes, well, you can cancel that common complex exponential to find the result that the complex amplitude of the voltage around any loop equals 0, which means it obeys KVL. And same thing for the currents. The complex amplitudes of the currents obey KCL. So we now have a very consistent picture. When the sources are complex exponentials, so they look like the Vn we've just had, it turns out all that we just discovered, that all currents and voltages are complex exponentials. If you had solved that differential equation for the input voltage being a complex exponential, you would have discovered that if you assumed V out was a complex exponential, yeah, you get that answer. It's a consistent solution. Once you have a solution to a differential equation, no matter how you got it, you know it's the only solution. That's the way differential equations work. So all sources and elements, and element voltages and currents, can be considered just to be complex amplitudes, because we're going to assume the source frequency is understood. We're going to assume the complex exponential is sitting there. That's the cancellation I mentioned. And when we do that, all elements can be considered as complex valued resistors. The technical word is they're an impedance. That is really, it makes our life a whole lot easier. Let's go back to our RC circuit. So we're going to talk about our RC circuit, and instead of it being out of real world values, we're going to consider it as being built out of impedances. So I want to be sure you notice something in the notation. Over here, this is a lowercase Vn of t. We're assuming that's Vn e to the j 2 pi ft. This is a lowercase v, which is going to be something which we know is going to be an uppercase v out e to the j 2 pi ft. So these are uppercase and these are lowercase. So what you do is you think about everything as being a impedance. All the resistors, capacitors, inductors are impedances. The source is a constant given by the complex amplitude of the complex exponential back here. So time is gone. There is no time variation in this circuit. And we have a V out. And now we want to figure out what the amplitude of the output is given the amplitude of the input. Well, now that everything's resistor, we can use voltage divider. What could be simpler? You're going to use instead of resistor values, we're going to use impedance values in our voltage divider. So, voltage divider says that the output voltage is equal to the impedance of the capacitor divided by the sum of the impedances of the resistor and the capacitor. Just like we had before with resistors. Plug in what their impedances are and simplify a little bit. We now know what V out is. It is equal to the amplitude of the source times a complex number, 1 over J2 pi FRC plus 1. So, what could be simpler? And now to complete the story, we now know that this is true. We put back in the complex exponentials. We, if you will, uncancel the complex exponential that was lurking in the setup from the very beginning. And now we know that when the input is a complex exponential, the output is also a complex exponential, where V out is equal to this quantity. We have solved the circuit for the case of a complex exponential source. That's the way the impedance game works, if you will. So, when the circuit consists of sources in any number of resistors, capacitors, inductors, it doesn't really matter. You can pretend the sources are complex exponentials having some frequency f, and then you consider each element to be an impedance, a complex valued resistor. And now you can use all the tools we've already had, voltage divider, current divider, series parallel rules, to figure out how the output's complex amplitude is related to the complex amplitude of the source. Okay, so I'm going to show you the consequences of this. You may be a little concerned that, what about this pretend part? Suppose my source isn't a complex exponential, which is usually the case. You're going to have a hard time generating a complex exponential with any real-world source. Well, it turns out we're not really going down a blind alley. This is going to open the door to a whole new way of thinking about things, and we'll get that in succeeding videos.